to the organizers for the opportunity to speak here. It's really an honor to talk at this and celebrating my name is Andrew Glensker. Yeah, so I'm going to be talking about the Hasse principle of Kummer varieties. So talking about new results on this using I guess what's known as the descent vibration method in a bit. So maybe I'll start by saying, so there's not on archive yet, but I've got a pretty complete draft. So if anyone's interested, feel free to email me and I can. So maybe let's just start with a little bit of an introduction to Hasse principle. So throughout the talk, K is going to be a number field. And suppose we have, say, some variety, let's say it's projective, whatever. Okay. Then we say that X satisfies the Hasse principle. Okay, which I'll abbreviate as AP. If having points over every completion of K is enough to conclude that there's points over K itself. So if X is everywhere locally soluble, so I'll abbreviate this. That's everywhere soluble. Is enough to conclude we have points over the number fields. Okay. And I guess Hasse's name is here from sort of the first example of positive result of varieties that satisfy the Hasse principle, which is varieties cut out by quadratic forms. So Hasse-Minkowski theorem. Says that if your variety is form, say, vanishing of some quadratic form in P to the n, so Q quadratic form in n plus 1 variables, so homogeneous of degree 2, and this satisfies the Hasse principle. So in particular case of quadratic form inside P2, this is saying that conics, so genus 0 curves satisfy the Hasse principle. As soon as you move away from this, there's quickly examples where this fails. So me just write down 2 of them, which will sort of be instructive. So I sort of move towards what I want to talk about, Kummer varieties. So maybe the first counterexample to the Hasse principle comes from following genus 1 curve. I'm going to write down 2 of these. The following genus 1 curves over Q fail the Hasse principle. So you have this y squared equals binary quartic, and inside some weighted projective space, which is maybe the first counterexample to the Hasse principle that I know. So this is due to Lind and Reichardt in I think the early 40s. And
I think the very first one was Hasse, actually. Hasse.
Oh, okay.
I think it was before.
Do you know what was the? You know what was the?
Yeah, so it's a counterexample to the norm principle that we.
Okay.
So for biquadratic, yeah, right. So that.
Okay, so hopefully we'll hear about this.
1937. Don't know what the date.
Yeah, this is maybe 1442. Yeah.
So,
yeah. Okay. So this genus 1 curve fails the Hasse principle, and there's also the very famous example of Selma. Plane. So I mean, in particular, as soon as you replace sort of a homogeneous degree 2 equation with a degree 3 one, you get counterexamples. So these fail Hasse principle. And as soon as you move from genus 0 to genus 1, you get counterexamples. Yeah, so I mean, this one in particular, there's some elementary argument using quadratic reciprocity to show that you don't have any Q points, which can be sort of quite constructively rephrased in terms of a Brownian obstruction on this curve, and I'll say a little bit more about that in a second. So this example is due to Sommer from, I think, sort of early 50s, like 51 or something. And I mean, it was this and examples like it studied by Sommer that motivated Castles to define what's now known as Sommer groups. And because those are going to appear when I talk about Kummer varieties, I want to maybe introduce a little bit from the perspective of counterexamples to the Hasse principle, what Sommer groups and Shepherd groups say. I think for concreteness, I'll mainly talk about two Sommer groups, elliptic curves. So you take an elliptic curve over your number field, then this sort of famous exact sequence you can use to try and understand what the rank of this curve is. And this relates sort of E over K mod doubles to the two Sommer group. Co-kernels, two torsion in the Shepherd group. Okay, so some finite dimensional F2 vector space. If you want to compute the rank of elliptic curve, probably the first thing you try to do is compute the Sommer group, and its dimension gives you an upper bound on the rank. And if you're lucky, this co-kernel will be trivial, and then you compute the rank, and otherwise you have to worry about how big this co-kernel is. So this is the Shepherd group. Which is conjecturally finite. And so I want to say sort of geometrically what these groups are, or how you want to think of these. So the Shepherd group contained inside the cohomology group coefficients in, I guess, the k-bar points of the elliptic curve. And so this is parameterizing the principal homogeneous basis for the elliptic curve, or if you like, think of this as parameterizing genus 1 curves with Jacobian isomorphic to E. Say Y. And in particular, the genus 1 curve has a point, if and only if corresponds to the trivial class in H1.
Yes, the isomorphism with the Jacobian should be part of the
Yeah, it's part of the data. Yeah, thanks.
Your font size is starting to get a little small.
Yeah, sorry. Okay, yeah, please keep saying that and I'll gradually up it. And if it shrinks again, I'll up it. Yeah, thanks. Yeah, so the isomorphism to Jacobian is part of this data. And inside here, there's the everywhere locally soluble guys. So the elements inside the Shepherd group, they're the genus 1 curves in here, where everywhere locally you have a point, and sort of non-zero elements are precisely corresponding to counterexamples to the Hasse principle, genus 1 curves, because you get the trivial element when you have a k point. And the Sommer group is measuring something similar. It's inside our cohomology group of coefficients with two torsion with the elliptic curve, and this is parameterizing the two coverings. E. So kind of the genus 1 curve map. Finite surject homomorphism down to E, so defined over K, which over K bar, so it's like a twist of the multiplication by 2 map on the elliptic curve. So over K bar, isomorphism, completing this diagram, the multiplication by 2 map. In case of this map pi is part of the data of the existence, this doesn't use it. exists something fitting in this diagram. And here, what the two-Selma group is looking at is things like this, where this curve y is everywhere locally. You can show that if you have an everywhere locally soluble two covering, then there's a natural way to write this as sort of y squared equals binary quartic form, and this gives you the well-known parameterization of two-Selma elements in terms of equivalence classes of binary quartic form. Sort of conversely, if you have a binary quartic form, then this naturally gives rise to a two covering of the Jacobian of the corresponding curve. So for example, this counterexample to the Hasse principle we have over here. If this gives a two-Selma element. It's naturally a two-Selma element for curve y squared is x cubed plus 17x. And because it's a counterexample to the Hasse principle, it's representing a non-trivial element in the Shaffer-Tate group. So this sort of cohomological machinery of Selma groups and Shaffer-Tate groups is kind of exactly describing counterexample to the Hasse principle for genus one curves, and finiteness, conjectural finiteness of Shah is saying that if you break up genus one curves depending on what their Jacobian looks like, you should only have finitely many counterexamples. Okay, the last bit before I sort of start talking about more general varieties, so the last bit of sort of structure I want to talk about in terms of where Selma groups and Shaffer-Tate groups are concerned is the Cassels-Tate pairing. So this is some alternating pairing on the Shaffer-Tate group. I'll denote CTP, so Cassels-Tate pairing. Evaluating Q mod Z, and well, it's can be shown. So this kernel is a maximal divisible subgroup of the Shaffer-Tate groups. In particular, if it's finite as expected, then this pairing is non-degenerate.
Will you tell us what this pairing is?
Sorry?
Can you define the pairing?
Sort of. So I'll say maybe part of what it is in a second. So it's a little bit complicated to write down various definitions. I can certainly define it at the end if you want. I'll say a little bit more about it in a second. Yeah. So what did I want to say about it? Maybe one thing that I want to use later. So this induces naturally a pairing on Selma groups. So for example, induces a pairing on the two-Selma group. Valued in half Z mod Z. So it's given by projecting into the Shaffer-Tate group, you land in a two torsion. By the Cassels-Tate pairing, you land in the two torsion of Q mod Z. Which detects whether element in the two-Selma group lifts under multiplication by 2 to the four-Selma group. So if do a two descent to try and compute the rank of your elliptic curve, and you suspect that there's some non-trivial elements in the Shaffer-Tate group kind of obstructing finding what the rank is, you can try and improve that bound by doing a four descent. Or sort of equivalent would be to try and compute the Cassels-Tate pairing on the two-Selma group to improve the bound on the rank. And so, for example, Tom Fisher has a really nice paper explaining when you represent two-Selma elements by binary quartic forms, how to compute explicitly the Cassels-Tate pairing on the two-summer group. And
When
the
you say
something,
kernel there, does it mean like the kernel of the map from cell 2 to Ham from cell 2?
yeah, I guess the left, I mean, left or equivalently right kernel of this pairing is this, yeah. Yeah, so in practice, you can compute what the Cassel state pairing looks like, so you can test which elements lift to the four-summer group or not. And so I think in our example, we can check that this counterexample to the Hasse principle, we're carrying around this pairs non-trivially with some auxiliary genus 1 curve, which you think is like a quadratic twist of this first one. But in particular, by exhibiting an element that pairs non-trivially with, you're necessarily showing that this has non-trivial image in the Shafarevich state group, and so it cannot have any points, any rational point. So one way to prove that this is a counterexample to the Hasse principle would be to compute this Cassel's state pairing and show that it's non-zero. And I mean, more generally, you know, as long as the Shafarevich state group is finite, then any element in here must pair non-trivially with something. And so that sort of non-triviality of the pairing will be a way of exhibiting the fact that this is a counterexample to the Hasse principle. And sort of whenever you do that, what you're doing is showing that there's a Brauer-Manin obstruction to the Hasse principle on this category. There's sort of one way to define this Cassel's state pairing is as a natural map from, say, this example. There's a natural map from the Shafarevich state group of E over K towards the Brauer group of whatever element you're taking here. And then what this pairing is a sort of tests whether the element in the Brauer group of C you get exhibits a Brauer-Manin obstruction or not on this curve of C. You sort of evaluate that Brauer element at local points and you sum up the invariance of the elements in the Brauer group at local points. That's probably as much as I want to say about how you define this. But yeah, in this way, what you show is that if the Shafarevich state group of elliptic curves is finite, then the Brauer-Manin obstruction is the only one to have rational points on genus 1 curve. Okay, any questions at this point before I start talking about Hasse principle? Yeah. What's the yeah. Yeah, maybe can I leave that and I've happily explained it at the end. Yeah, okay, so I talk about Hasse principle Kummer varieties. So let me say what I mean by a Kummer variety. So, okay, the basic case is as follows. So suppose I have some abelian variety. Okay, then, well, over an algebraically closed field, sort of all I mean by Kummer variety is you quotient by the action of plus or minus 1. So say over K bar, Kummer variety, I just mean the quotient of A by action of plus or minus 1. Maybe this gives you something singular and you want to use some appropriate desingularization of this to get a smooth projective variety. So in dimension 1, say, you've got elliptic curves. So plus or minus 1, that just sends y to minus y. So the quotient map here is just mapping to P1 by the x coordinate. So you're getting the projective line. You can show that in dimension 2. So here already this quotient was smooth. Dimension 2 and higher, you get singular points. The image of the two torsion of the abelian variety, you can blow up once at each of these, and then you get a smooth projective variety. And dimension 2, you can show that you get K-free surfaces this way. one of the main motivations for studying Hasse principle for Kummer varieties is in the case of surfaces, we're saying something about the Hasse principles on K-free surfaces. Something it's quite hard to say about in general, and where there's lots of conjectures, but not so much known of what to expect. Okay, so this is so far not so interesting. If you take, being variety has at least one point, map it down to the quotient, so you'll get points on these quotients. So you want to cook up something slightly more interesting to ask about the Hasse principle, and so you do that as follows. So we're just going to take some sort of twist of this. So you start by fixing some class alpha inside this gamma cohomology group where the two sum group lives, H1 with coefficients in the two torsion. So associated to this, maybe even, so just as the case of elliptic curves, the two covering of the abelian variety. Corresponding to alpha, you have a two covering. Y alpha. So you can show by commutativity of this diagram that multiplication by -1 on A, when you transport it across this isomorphism, you arrive at an involution on Y alpha, which is defined over K again. Okay, defined over K, and then you just take the quotient by that involution, and you do the same desingularization before, constructing in this way a twist of this variety. So maybe let me squeeze it up here. X alpha, the Kummer variety associated with class. Yeah. There's the quotient by this involution, and then you take a minimal desingularization. Okay, and these sort of Kummer varieties associated to classes in this Gauss cohomology group with coefficients in the two torsion, these are the varieties that we're going to study Hasse principle for. And there's a general method going back to Swinnerton Dyer for how you can do this. So you can say that you can study existence of racking points X alpha via what I call the descent vibration method. And this has been done in a series of papers by Swinnerton Dyer, Skobogatov, Hasse. The original method goes back to Swinnerton Dyer, but was used to study a slightly different question. Swinnerton Dyer and Skobogatov together did some initial cases of this, and then Skobogatov and Hasse pushed this further, and then Hasse has a paper by himself, pushing it again further in a slightly different direction. So let me state one result, which is what comes out of the joint work of Skobogatov and Hasse, and that's what I'll give it to MA, and that's what I want to sort of talk about with this and the generalization of this of mine. Due to Hasse and Skobogatov in 2015. So it says the following, and this is the same sort of shape of all the other terms. So suppose your beam variety is principally polarized. So our main examples are coming from Jacobians of curves, which certainly are. Take your class. It's going to define the Kummer variety. And we write G to be the Gower group of the two division field, the Sabinian variety. Then, okay, so assume some things that are filling later. You first write what the punchline is going to be before I add in sort of a bunch of assumptions. Then what you show is that the Hasse principle holds for the corresponding Kummer variety conditional on finiteness of Shepard state groups for some auxiliary abelian varieties, and what those auxiliary abelian varieties are quadratic twists of this starting. Which, okay, maybe is somewhat reasonable, because to get a grip on the obstructions to the Hasse principle for genus 1 curves already, you need some finiteness of auxiliary Shepard. Okay, so what are these assumptions?
I have a question.
Sorry, yeah.
I'm confused with the contrast to the one-dimensional case where it wasn't that the Hasse principle held, but that the Brouwer name was the only obstruction.
Yeah, and I think so. I mean, there's a conjecture of Skorobogatov that the Brouwer-Manning obstruction should be what's controlling Hasse principle, counterexamples of Hasse principle, K precepts. So what it turns out, and sort of, well, for the assumptions I'm about to state, the paper of Skorobogatov and Zahin, which is basically that there's some algebraic assumptions here which I haven't written down yet, and they in particular imply vanishing of a certain part of the Brouwer group. And under those assumptions, you can show that the Hasse principle is sort of unobstructed. So in some sense, this is proving that the Brouwer-Manning obstruction is what controls the Hasse principle. It's just is kind of hidden behind the scenes in the vanishing of some part of the Brouwer group of this concept. Variety, thanks. So, yeah, so what are these assumptions? So there's a technical assumption, let me say, I can go into, but I prefer not to, on what this class looks like to start with. It has to be particular, sort of unramified at a certain place where you have a particular reduction type. And then there's 4 assumptions I'm going to have difficulty fitting in on what the Gower group of the 2 division field, or what the 2 division field is. So okay, so the first one, so all of these 3 are going to say that the G is sort of somewhat large. So I want the 2 torsion to be simple as a G module and to have only scalar endomorphisms commuting with this G action. And they want existence of certain particular elements. So there wants to be some element in G fixing no 2 torsion points. And some element fixing a 1-dimensional space. So all of these are kind of in the spirit that G should be large. They're satisfied in particular by, say, full symplectic group of automorphisms preserving the wave pairing. And then this last one says that you should have no classes inside this cohomology group that vanish on restrictions of the 2 division. So this side additional set.
these technical assumptions are not supposed to be necessary? I mean, you expect that you can just erase it, you want to.
I'm not sure exactly. Yeah, so there's a step where you genuinely,
But that's the proof. They.
yeah, of course it's used in the proof, but it's also not clear to me that so. So the work of Harvard, so all the other works that I mentioned at the start here, they have they treat the case where you have all of your two torsion defined over the ground field. And the final work of Harpash, he finds that you genuinely can get a Brownian obstruction in that instance. And it's not clear to me that, yeah, I guess this should not be necessary because I think we prove, as I mentioned earlier, that you shouldn't get an obstruction to the Hasse principle in this case, but yeah, I don't know how to remove it, and it's yeah.
Three contradictory.
Sorry?
Different G.
What?
Different.
Oh, sorry, there's like a G
Gs.
primed or something.
G.
Yeah, sorry. Oh, it is, yeah.
Yeah.
What's the S in HS?
Oh, so there's a theorem of Harpash and Scorbigato. There's the initials of it.
Can I just clarify what you just said? So if it has full two torsion, you're saying it's no, it's can't be true.
And so in full two torsion, there's instances where you genuinely get a Brownian obstruction, and Harpash pulls off what I'm about to describe, this descent vibration method, but he doesn't pull it off to show that the Hasse principle holds. He pulls it off to show that the Brownian obstruction is the only obstruction to Hasse.
It's this, is it this 4 that is giving you the vanishing of the?
I think it's mainly this one. The sort of fact that you have, yeah, I think it's mainly the first one. That is an assumption.
You said that the 1 through 3 are satisfied for the complex.
Yes, that's right. Yeah, that's true. And so, well, the theorem that I'm about to state of mine in a second is going to in particular allow the full symplectic group. No, this doesn't. So you want
Sorry, what did you just?
when you have, so there's also sort of orthogonal work when you have all your two torsion defined over the base field, and then you can get obstruction. Yeah, sorry, thank you. Yeah. Yeah, any more questions of this?
Explain what dim A of 2 equals 1 means. Like A of 2 is a 0-dimensional scheme.
This is a vector space.
Is it all defined over F2 or it's like
So I take A2 as like a Galois module or something, and I want
over K bar?
okay, so look at the K bar points of the
Okay, thanks.
and I want yeah, Galois automorphism of that fix is just aligned. So yeah, when I write A2, I mean, I guess I think of the K bar points as a Galois module rather than as a okay, so I'll make some remarks. I think quite a lot of them I already said. So yeah, first of all, so these assumptions 1 to 4, they hold in particular. So one natural case where they hold is for the Jacobian of some hyperelliptic curve of odd degree. Where the Galois group of F is as large as possible. So in particular, in the sort of one of the most interesting cases where you're saying something about K-free surfaces. So if you have a y squared equals quintic, so genus 2 curve with a rational bias stress point, and sort of with respect to that restriction, the Galois group is as large as possible, then these assumptions will hold. Sorry? They don't hold for AN because I think you can show that you always fix an even dimensional subspace of the two torsion for AN, yeah. Yeah, but so they fail. So in particular, this part 4 fails for G, the full symplectic group, P2 GF2, which is sort of as large as it can be with respect to being as repolarized, preserving the wave pairing. Reduce dimension of A. And it also fails for Jacobians of even degree hyperelliptic curves with large Galois group. And the reason for this is that in both cases you have some distinguished class inside this H1. So in both cases, you can show that this H1 generated by a class that I'll call C, which is parameterizing, depending how you want to think of it. It's parameterizing either quadratic forms whose corresponding bilinear pairing is the wave pairing, quadratic refinements of the wave pairing. Or if you like, more geometrically, this parameterizing symmetric line bundles inducing the given principal polarization. The Jacobians is corresponding to beta characteristics. So sort of while these first three assumptions are saying that everything's good as long as your group is large enough, this fourth one is saying, well, except it shouldn't be too big because you want to have sort of a quadratic refinement of the wave fixed wake up. And so what I was interested in is trying to see if you could push this to get rid of that assumption so you can do the group, take G to be as large as possible. And I guess that's what I want to talk about. So theorem is the same. Same as this theorem A. Maybe I'll call this theorem B. Okay, but we'll see. Sort of as a byproduct of method, I remove this assumption 3. You no longer need sort of a one-dimensional space fixed by some element. And replace 4 by, I guess, 4 primed, which says that you allow SH1 to be generated by this class, which may or may not be 0. But yeah, so in particular, you now allow the full symplectic group, and so in the case of Kummer surfaces, you allow ones constructed from Jacobians of y squared equals degree 6, where the degree 6 polynomial has Galois group S6, so sort of as large as it can be in some sense of generic. Yeah, maybe one thing, so we'll see in a second how it sort of comes down to understanding behavior of two Selma groups or two power Selma groups in quadratic twist families. That's why you want this finiteness of Shapiro J groups in quadratic twist families. And these conditions here are sort of something that would guarantee that Alex Smith's method for understanding two power Selma groups in quadratic twist families would work. One of my motivations for studying this problem was to try and see what's involved in moving beyond that. And in particular, this is something that would not currently be allowed by those methods. And we'll sort of see the relevance in this. Okay, so how do you go about understanding rational points on these Kummer varieties? So you do this by covering this variety with a family of sort of Tors's under abelian varieties. Particularly, you do this by quadratic twisting the original two covering that we started with. So if you take some d k cross modulo squares associated to this, you have the quadratic twist. Equal AD, and okay, this is typically a new abelian variety defined over K again, but property that it has is that at least the two torsion is isomorphic to two torsion that we started with, so either as a group scheme or as a Gauss module. And when you construct the quadratic twist, you twist by multiplication by -1, which is doing nothing on the two torsion. So in particular, what we can use this to identify H1 coefficients in A2 with corresponding thing for the twist. So we can view this class now, giving something on the twist. And we can form the corresponding Kummer variety out of this, which corresponds to L2 covering twist. And when you take this quotient, what turns out is that you just get back the original Kummer variety that we started with. So the reason, I guess, is that when you take this Kummer variety, at least geometrically, you're quotienting by the action of plus or minus 1. When you form this quadratic twist, you're twisting by plus or minus 1. So once you kill it, you expect that you've done nothing in the quotient. So in particular, this Kummer variety we're interested in is covered now by a whole family of two coverings for sort of varying abelian varieties. So sort of family of clauses for abelian varieties all mapping down to the same variety. And going to use this whole family to sort of control rational points on this common quotient. So one dilemma to show that that's something reasonable is the following. So suppose we have a rational point on the Kummer variety, then that's actually equivalent to having a rational point on one of these covering the total. We have a rational point on one of these varieties, you can project it down to the Kummer variety. In general, a rational point in the Kummer variety, you don't expect it to lift to a given covering, but it does turn out to lift to one of these terms. So the way to think about this is you start with your original two covering, mapping down to this Kummer variety. So you have a point here. You just look at the fiber over this, and there's a form sort of Q and iota of Q's, it's the involution of quotient by, where Q might not be defined over K, it's defined over the algebraic closure, but certainly the set is defined over K. And the Gauss action on the set of size 2, setting out a quadratic extension for you. When you twist by that extension, you just check that you untwist the Gauss action on this fiber. And so this point lifts to the corresponding. So that's sort of how that lemma is proven. So sort of in that way, you reduce understanding rational points in this Kummer variety to understanding sort of rational points on this family. Okay, and based on that observation, here's a sort of strategy of grouping this theorem A of Scarbogatov and Harpash. And I guess the strategy that I'm outlining is what's sort of known as the descent vibration method. So it's got two main steps. So firstly, which I won't say too much about, but so using this lemma. So I guess you can apply that same argument, not just over K, but over any field extension of K. In particular, you can use it over completions. So using the lemma applied to completions and an argument involving the vibration method. You show that Kummer varieties ever locally soluble if and only if there exists a D0 where the given homology class lies inside the two Selma group twist by D0. So what's sort of going on here? So this is saying that there's a sum twist where this covering variety is everywhere locally soluble. What the lemma gives you is that for each completion, there'll be some quadratic extension of the completion where the point lives. And this is saying that I can kind of patch together those different quadratic extensions over completion to a single global one. And in general, maybe you don't expect to do that, but really you only need to kind of apply that lemma at finitely many places of bad reduction for the original abelian variety. And then you sort of know everything that's going on at the remaining places, and you have enough flexibility to find a single global twist that's sort of approximating these local.
Can you say again in words what the vibration method means?
Maybe not. But it's sort of what I just said. You have these local, in this instance, you can do it rather more explicitly. You have, for each completion, you have sort of a D0 comma V where the point lifts, and you want to patch them together into a global one. And there's sort of various techniques involving partiality, say, which tells you when you can approximate a collection of local characters with a global character. Sort of what's going on. Yeah, it's a special case of a more general method that which I don't feel well qualified to speak about. Okay. Then, so the second step, so you find some twist where this class lies in the two Selma group. And then you start from there. And the idea is to successively alter this D0 to change in a controlled way the two Selma group of the corresponding twist. So you just say that using a twisting procedure of Mason Rubin, so construct sequence E1, E2, so on up to some Tn, which changes the Selma group in a controlled way. So, where does this two Selma group live? So it lives in H1 with coefficients in two torsion of the twist, but this is just the same as the two torsion of the original abelian variety. So you can view sort of two Selma group of every twist inside a common space. There's sort of starting point for every kind of result about behavior of two Selma groups in quadratic twist families. So when you view all these in a common space, what you're doing is you're shrinking successively these two Selma groups. So on until you arrive at some Pn, where we find this two Selma group is generated by the starting class and that class alone. And so these conditions on the two torsion, in particular, sort of these two conditions are what's allowing you to do them. Okay, but then you're done. Why is that? So. Well, the Castle's tape pairing on the Shepard's tape group, the twist is alternating. And we're happy to assume it's non-degenerate because all things are conditional on finiteness of Shepard's tape groups. So it's non-degenerate. Shepard's tape group of the twist is finite. And whenever you have a non-degenerate alternating pairing on a finite abelian group, that group has even dimensional two torsion. Some general fact. To start by saying it's even. Maybe you've got a group that's one dimensional, so projecting onto something that's even dimensional, so this had better be zero. So the given class, this has to map to zero inside H1, corresponding to covering has to have a rational point, and you can project that down to the correct. Say y alpha Tn as a rational. Yeah, in particular, solar vector. Okay, so in the last sort of 5 and a bit minutes, say, well, what goes wrong with that strategy in the case of this theorem B of mine, and what we do to resolve them. So there's two problems. So the first one is this class C, parameterizing quadratic refinements of the Bay pairing. You can show that this just lies like the two-summa group of every single twist. So it's just stuck inside all of these two-summa groups. So sort of can only hope, could only hope for them. We could this Christian procedure to find some Dn where the two-summa group contained this class C and this class alpha that we're interested in. Suppose they're different, and then you're really stuck because you have a two-dimensional summa group, and there's no way to conclude from there that the Shapiro tape group should be trivial. But actually, even if we could find this being one-dimensional, we still have a problem because we said the Castle's tape pairing is alternating, which it is, under the assumptions of this theorem A, but in general, that's not true. So the second problem is that this sort of lovely theory of Kuhn and Stoll measuring the failure of the Castle's tape pairing to be alternating on principally polarized abelian varieties. So in particular says any D and X in average tape group with the corresponding twist. The Castle tape pairing evaluated on the diagonal element, X of itself, that's the result, pairing X with this distinguished class C. So in particular, this pairing is alternating precisely when C vanishes. So sort of both of these concluding steps fail. You cannot get the summa group as small as you'd like, but even if you could, you wouldn't be able to conclude necessarily. Basically what we do instead is the same as what I said right at the start. If you trying to compute ranks and the two sample group isn't enough, you try and see if you can win on the level of the four sample group. And to do that, you want to understand what the Castle's tape pairing looks like on the two sample group. So I guess the sort of following steps. So instead of trying, okay, so the first step we found, I don't know if I wrote it off, you find a twist using everywhere local solubility of the Kummer variety, you find a twist where this given class lies in the two sample group. So that just works the same. We're going to impose something else as well. And what we're going to want to do is to impose at the start the to infinity sum rank of this twist is odd. And so I have sort of an earlier paper where I study the behavior of parities of two infinity sum ranks in quadratic twist families and show essentially that they're governed just by what the twist looks like at finitely many places, sort of independent of the twist. It's just the places of bad reduction for the original abelian variety is something you expect from root numbers, but which you can prove sort of unconditionally the two infinity sum ranks. And then the second step. So instead of trying to shrink the Selma group, construct sort of using similar observations of Mason-Rubin, a whole family of twists where you get identical to Selma group. So construct an infinite family twists such that if he is in this family, then it has the same parity to infinity sum rank and the identical to Selma group is this one we found above. So you have a whole bunch of twists where the two Selma group is unchanging, but you might expect that the Castle's tape pairing on the two Selma group is changing inside this family. And indeed, so that's what happens. So we then study the variation of the Castle's tape pairing on this common two Selma group. Okay, so sort of using, well, ideas of Alex Smith, also related to ideas of Harpash in this early paper, because that I mentioned, and some ideas of mine from this paper on parity of two infinity sum ranks. And so basically what I end up showing, but don't have time to state, is that as you vary over this family, the Castle's tape pairing takes sort of every possible form it can, in the sense that if you just write down the structure that the Castle's tape pairing is supposed to have. So I don't know if I rubbed off. Yeah, this from Stoll. So every pairing satisfying this and one further condition about what he pairs with itself, you just range over all possible pairings as you range over this family. So sort of conclude from that, sort of the final step is to show the sum be inside this family I construct, where alpha is the unique element of this common two Selma group. Lifting, or in the kernel of the corresponding Castle's tape pairing, so lifting. If it's unique, if alpha is a unique element lifting to the four Selma, and we know the two infinity Selma rank is odd, then that forces alpha to be coming from a rational point that leads to assuming finiteness of Sheffer. So again, you conclude that it has to map 0 inside the Sheffer K group, the corresponding twist, and then in particular that the corresponding the Q covering has a rational point, and that again establishes that. Yeah, and I think that's all else.